Hey there, and welcome back to the Deep Dive, your shortcut to being well-informed. Today we're diving headfirst into a realm of our digital lives that's everywhere you look, yet often completely invisible: the application layer. If you've ever typed a URL, sent a message, or simply streamed a video, you're interacting with what tech pros call Layer 7. It's where your apps meet the network, and it's also, unfortunately, a prime target for cyber threats. We've got a real treasure trove of information today, specifically on how organizations prepare, respond, and fight back against incidents at this crucial layer. We're going to unpack the vulnerabilities, the defenses, and the step-by-step strategies for keeping our digital interactions secure. Okay, let's peel back those layers and see what makes this space tick.
Indeed. We'll be exploring the very top of the OSI model, which essentially translates to where you directly engage with digital services. What's truly fascinating is how this layer, which seems so intuitive and, frankly, user-friendly on the surface, becomes an incredibly complex and dynamic battleground for cyber threats beneath. Our mission today is to demystify these complexities for you, highlight the most common vulnerabilities you'll encounter, and, perhaps most importantly, reveal exactly how organizations, and by extension, you can prepare and respond when things inevitably go wrong at this vital juncture.
Right, we're talking everything from the fundamental protocols that power your web browser to the, surprising ways attackers exploit them. And then, most crucially, the detailed, battle-tested strategies for defending our digital fortresses. Get ready for some eye-opening insights and real-world examples that might just make you think differently about every click, tap, and swipe you make online. So let's start with the absolute basics. When we talk about the application layer, or Layer 7 in the grand scheme of the OSI model, what are we really referring to? It sounds technical, but it's the part we all experience every single day, isn't it?
Absolutely. It's the human-facing part of the internet, the one you interact with directly. If you think of the internet as, say, a multi-story building, Layer 7 is the penthouse suite, the floor where all the customer-facing activity happens. It's where applications like your web browser, your email client, your social media app, or that game you're playing, they directly interact with the network to provide you a service. It's the topmost layer of the OSI model, responsible for presenting network services in a way that end-user applications can, understand and use. It's called the application layer, simply because it's where your application processes request network services. What's interesting here is that it's the most abstract layer. It deals with the representation of data for the user. So when you open a web page, send an instant message, or post a photo, all these intuitive user-level interactions are made possible and governed by Layer 7 protocols.
And our deep dive materials go into quite a bit of detail on the specific protocols that live here. Could you walk us through those and perhaps give us why it matters for each, explaining why they're so central to Layer 7 operations and security?
Certainly. The protocols we rely on daily are the very backbone of these digital interactions, and understanding them is key to grasping their vulnerabilities. First up, we have HTTP, the Hypertext Transfer Protocol, and its secure counterpart, HTTPS. These are basically the fundamental languages of the World Wide Web. HTTP, by design, is a stateless protocol. Think of it like a forgetful waiter. Each request you make, say, clicking a link or submitting a form, is a brand new interaction. The server doesn't inherently remember your previous order or who you are from one request to the next.
Okay, stateless, so it forgets everything immediately.
Pretty much. The simplicity makes it efficient, sure, but it also means that managing things like your logged-in session, keeping items in your shopping cart, or remembering your preferences becomes a complex application-level challenge. This challenge is often solved by technologies like cookies, which, themselves become targets for attack. Now, HTTPS adds that crucial S for secure layering encryption, usually SSL or TLS, over HTTP.
Right, the little padlock icon.
Exactly, and that encryption is vital at the application layer, especially for sensitive data like login credentials, banking information, or personal details. It prevents anyone from eavesdropping on your conversation with the server. Without HTTPS, your data would be sent in plain text, easily intercepted. This huge risk is precisely what drives the industry-wide shift to HTTPS everywhere.
Makes sense. What's next on the list?
Next, we have DNS, the domain name system, often dubbed the Internet's phone book. It translates human-readable domain names like google.com into machine-readable IP addresses.
Oh, phone book, I get that. But how is it Layer 7? Doesn't that feel more like network infrastructure?
That's a good question. While it feels like a foundational network service, the true Layer 7 insight is that DNS interactions are initiated by applications on behalf of users. When your browser tries to reach a website, it first asks the DNS where to find the server. This makes it a surprisingly vulnerable point for application-aware attacks like, say, cache poisoning, which can redirect you to malicious sites, directly impacting your user experience. And without DNS, you'd have to type complex IP addresses like 172.217.160.142 every time.
Right, totally impractical. Okay, DNS. What else?
Then there's SMTP, the Simple Mail Transfer Protocol. This is the engine for sending and receiving email. It's how your email client communicates with mail servers, facilitating virtually all business and personal communication. Its critical role makes it a, well, frequent target for spam, phishing, and various forms of email-based attacks.
Email security, always a big one.
Definitely. We also consider FTP, the File Transfer Protocol. As its name implies, it's for transferring files between clients and servers. While maybe less common for everyday users today thanks to web uploads and cloud storage, FTP remains widely used for large file transfers in web development, for deploying applications, and in many enterprise settings. Any unencrypted FTP transfer is a Layer 7 risk, as credentials and data can be easily intercepted.
Gotcha. Still relevant in certain contexts.
And finally, a rapidly expanding area of Layer 7 are application-specific APIs or application programming interfaces.
APIs, right. They seem to be everywhere now.
They are. Think of an API like a standard menu at a restaurant. You don't go into the kitchen yourself. You tell the waiter exactly what you want from the menu. That's your request.
And the kitchen prepares it and sends it back. The response.
Precisely. APIs are how different software restaurants, like your mobile app and a cloud service, talk to each other, using a predefined menu of requests and responses. They are truly the glue for modern distributed applications, cloud services, mobile apps, everything. Their proliferation has, well, inadvertently created a new and vast attack surface for cybercriminals. Understanding these protocols, HTTP, DNS, SMTP, FTP APIs, it's the first step because, as we'll see, many critical Layer 7 incidents stem directly from vulnerabilities within these very communication methods.
With all that complexity, it's perhaps inevitable that where there's opportunity for applications, there's also opportunity for exploitation. So let's turn our attention to the specific threats that target this crucial layer. Imagine you're checking your bank balance and suddenly, without you doing anything, a transfer is initiated. Or you click a link and your login credentials are stolen by a page that looks identical to your bank. These are the chilling realities of Layer 7 attacks, and it's where our deep dive gets truly eye-opening. What are some of these primary threats that target the application layer?
Right. The threat landscape at Layer 7 is dynamic, it's constantly shifting, but several categories of attacks remain consistently dangerous and, frankly, pervasive. These are often direct assaults on the logic, the design, or the implementation of applications themselves. First, we have web application attacks. This is a very broad umbrella term covering any attack targeting applications delivered via the web. This includes exploits against web servers themselves, the application code, underlying databases, or even client-side components running within the user's browser.
So pretty much anything you interact with through a browser.
Largely, yes. The sheer accessibility of web applications, think about how many services you use through a browser daily, makes them a prime target. The widespread adoption of web-first platforms for almost all businesses means virtually every organization is exposed to this category of threats.
Okay, broad category. What about more specific types?
Then there are injection flaws. This is a classic, yet still incredibly prevalent, attack vector. The core idea is simple but devastating. Attackers insert malicious code into data inputs, like a search bar or a login field.
Things you type into.
Exactly. And the application then trusts that input and processes it as legitimate code. SQL injection, for example, allows attackers to manipulate database queries, potentially revealing, altering, or even deleting sensitive data. Command injection, another form, allows for the execution of arbitrary commands directly on the server hosting the application.
Can you give an example? How does that actually work?
Sure. To give you a concrete example, imagine a login form where instead of your password, a hacker types something like OR11. This malicious input, if the application isn't properly secured, could trick the database into thinking it's a valid query, thereby bypassing authentication entirely and letting the attacker in.
Wow. Just by typing something weird in a box.
Essentially, yes, if the application isn't built securely. Another common threat is cross-site scripting, or XSS. This is a client-side vulnerability, meaning the malicious activity typically occurs in the victim's own web browser, not directly on the server.
So it runs on my machine, not theirs.
That's the idea. Attackers inject malicious scripts into web pages that are then surfed to and viewed by other unsuspecting users. These scripts can then do a number of things. Steal session cookies, which could let the attacker impersonate you.
Without needing my password.
Correct. They can also deface websites or redirect users to malicious sites, all executed within the victim's browser context. Picture a malicious comment on a popular blog. It might contain XSS code that then runs in your browser when you view that comment, potentially stealing your session.
Okay, that's sneaky. What about CSRF?
Closely related is CSRF, or cross-site request forgery. Here, the attacker tricks a victim's web browser into performing an unwanted action on a trusted site where the victim is already authenticated. The attack works by exploiting the trust that a site has in your browser session. So, if you're logged into your online banking portal, an attacker might craft a malicious link or embed a hidden request on another, seemingly innocuous site. If you click that link or simply visit the malicious page, your browser, still authenticated with your bank, might unknowingly initiate a money transfer from your account.
Whoa, so I didn't even visit the bank site, but something happened there.
Exactly. You interacted with a different site, but an action was performed on your banking site because your browser was already logged in and trusted there.
Okay, that's quite subtle. And APIs, you mentioned them earlier.
Yes, API abuse is also a rapidly growing and significant threat. With APIs being the fundamental building blocks of modern apps, attacks against them are increasingly common. This involves exploiting weaknesses in API design, implementation, or configuration. These weaknesses could range from broken authentication mechanisms where attackers bypass logging controls to excessive data exposure where APIs just return way more information than necessary.
Like leaking extra data?
Precisely. Attackers can also exploit vulnerabilities like rate-limiting bypasses to flood an API with requests. Through these methods, attackers can scrape vast amounts of data, perform unauthorized actions, or simply disrupt critical services, leading to denial of service.
So hitting the application's back end directly.
In essence, yes. And finally, the nightmare scenario for many organizations: zero-day exploits. These are vulnerabilities in software that are completely unknown to the vendor, meaning there's literally 0 days for them to fix it before an attack occurs.
Because nobody knows about the hole yet, except the attacker.
Exactly. Attackers discover and exploit these before any patches exist, making them extremely difficult to defend against with traditional, signature-based methods. Their impact can be widespread and severe, as we've seen in some major high-profile breaches, causing significant damage before anyone even knows what hit them.
That's a lot to contend with. It really drives home why this Layer 7 focus is so critical. So, with these sophisticated attacks in mind, let's say one of them actually succeeds and an application is compromised. What does an organization do? Our source material emphasizes detailed incident response strategies. How do these structured approaches fit in, especially for Layer 7, which is so focused on application logic?
This is precisely where proactive planning becomes paramount. You can't just react in a crisis. You need a well-defined blueprint, a clear set of actions ready to go. Incident response strategies are developed to provide systematic approaches to managing the aftermath of a security breach. Our research highlights that these strategies are not generic, but are specifically tailored around the types of attacks we just discussed: web application attacks, injection flaws, XSS, CSRF, API abuse, 0 days.
So a specific plan for each type of attack.
Ideally, yes, or at least categories of attacks. The core idea is a structured approach to addressing and managing the aftermath. For Layer 7, this means understanding how application-level vulnerabilities lead to incidents and how to target our response to that specific layer. It's not just about network connectivity. It's profoundly about maintaining application integrity and protecting the sensitive data that applications process and store. These strategies are not just theoretical concepts, they are operational, designed to provide concrete, actionable steps under pressure.
And these aren't just ad hoc, improvisational responses, are they? The materials mention a strong alignment with industry standards like NIST, SANS, and ISO. Why is that alignment so important?
That's a truly crucial point. Adhering to established frameworks ensures a mature, consistent, and therefore more effective response across any organization. Think of them as universally accepted playbooks for cybersecurity. NIST, the National Institute of Standards and Technology, for example, provides a widely adopted framework. NIST SP 800 Test 61 for computer security incident handling. This framework breaks down incident response into clear, manageable phases: preparation, detection and analysis, containment, eradication and recovery, and post-incident activity. It gives organizations a logical roadmap.
A roadmap, okay. What about SANS and ISO?
SANS or SISMN Audit Network Security is renowned for offering practical, hands-on guidance and certifications. They're known for providing highly actionable methodologies and detailed templates. Then there's ISO, the International Organization for Standardization, with standards like ISO 27035, which provide international guidelines for information security incident management.
So using these standards brings consistency.
Exactly. These standards provide a common language and a set of globally recognized best practices. They ensure that incident response isn't reinvented every time. For Layer 7, this means having standardized procedures for things like meticulously analyzing web server logs, tracing specific API requests, conducting thorough database integrity checks. They help establish repeatable, predictable processes for handling these specific application layer threats. Imagine a global company where each region handled incidents differently. Chaos. These standards ensure a unified, predictable, and compliant response. It provides a baseline for effective operations.
Before you can even begin to respond, you have to know something's even happening. And with Layer 7 attacks often cleverly blending into legitimate user traffic, how do organizations effectively detect and monitor for these sneaky application layer threats?
Precisely. Detection is truly the first line of defense, and our materials emphasize its paramount importance. Effective detection and monitoring at the application layer are critical because, as you noted, these attacks often look like legitimate user activity. Unlike a direct network intrusion, which might have obvious traffic anomalies, a Layer 7 attack often uses valid protocol structures, but with malicious content or intent. Much harder to spot initially.
So you're looking for subtler signs.
Yes, we're really looking for subtle anomalies in how applications behave and interact with data, not just raw network traffic spikes. This requires a comprehensive and layered approach to monitoring.
What are the key tools or techniques that our sources highlight for both early detection and in-depth forensic analysis at this application layer?
Our research specifically highlights two incredibly powerful methods that serve both for early detection and crucial post-incident forensic analysis. First, log analysis. This involves meticulously scrutinizing application, web server, and database logs for suspicious activity. This is far beyond a cursory glance. It means setting up sophisticated systems to aggregate and analyze vast amounts of log data from every component: web servers, application frameworks, databases, API gateways.
So collecting logs from everywhere the application touches.
Everywhere. You're looking for subtle cues, unusual error codes, unexpected request patterns, a flurry of failed logins from specific IPs, unexpected data modifications. For potential injection flaws, you'd meticulously search for unusual characters or commands embedded within input fields. For API abuse, maybe sudden, abnormal spikes in requests from a single source, or an unusually high number of requests to a particular API endpoint.
Can you give an example?
Sure, a sudden surge in database errors immediately following a web form submission could be a strong indicator of a SQL injection attempt. Or repeated failed logins from a single IP address over a short period might signal a brute force attack against an application's authentication.
Okay, logs are one piece. What's the other?
Second, we have packet capture interpretation. While logs tell you what the application recorded, packet captures show you the raw communication, the actual bits and bytes moving across the network. This involves using specialized tools like Wireshark to inspect the actual HTTPS requests, DNS queries, SMTP commands, or API calls as they happen or retrospectively.
So looking inside the actual data being sent.
Exactly. For Layer 7, you're not just looking at IP addresses and ports, but the actual content of the application-level data within those packets. Things like manipulated HTTP headers, anomalous data payloads, or unexpected commands embedded within a legitimate-looking request. This is crucial for understanding the exact sequence of an attack, what data was potentially exfiltrated, or precisely how a zero-day exploit was delivered. It offers irrefutable evidence.
So it's about looking at both what the application itself reports from within and then what's actually moving across the network wires. That comprehensive approach makes perfect sense. Now, once you've detected an incident, the clock is ticking furiously. You need to act fast and decisively. Our materials detail incident response strategies, including specific critical steps for containment, eradication, and recovery. What does that look like when you're dealing with a Layer 7 compromise?
Right. This tripartite approach, contain, eradicate, recover, is central to any effective incident response plan, and it's particularly nuanced at the application layer. These are structured, step-by-step operational responses developed and aligned with industry standards like NIST, SANS, and ISO, designed to mitigate damage and restore normal, secure operations. These three phases are the actionable core.
Let's break down containment first. When an application is compromised, what's the immediate goal? Is it always about shutting everything down?
Containment is all about stopping the bleeding. The immediate priority is to limit the damage, prevent the incident from spreading further, and minimize the impact. A full shutdown might be necessary sometimes, but often it's more surgical. At Layer 7, this involves several critical actions. First, isolating affected applications or services. This could mean swiftly taking a compromised web application offline, isolating a specific API endpoint being exploited, or blocking network access to a database being injected, cordoning off the infected part.
Okay, isolate the problem area. What else?
Second, blocking malicious traffic. Organizations use tools like web application firewalls, WAFs, to block specific attack patterns known SQL injection strings, XSS payloads, brute force attempts. They can also block malicious IP addresses identified from logs or packets.
Using the way as a shield.
Precisely. Third, disabling vulnerable functionality. If a full shutdown isn't feasible due to business needs, teams might temporarily turn off a specific feature, module, or even an input field within the application that's being exploited, closing the immediate attack vector. The inherent challenge here, and it's a big one, is to contain effectively without causing undue business disruption. You need to identify the exact scope quickly using forensic data.
And once the bleeding is stopped and the threat is contained, you need to get rid of it completely, right? That's eradication. How does that work at the app layer?
Exactly. Eradication is about comprehensively removing the root cause of the incident and ensuring the attacker's presence is completely eliminated. For Layer 7, this involves patching vulnerabilities, applying security patches to known software flaws that were exploited, like the Log4Shell example needing urgent patching.
Fixing the known holes.
Fixing code flaws. For attacks like injection or XSS, developers must directly fix the vulnerable input validation or output encoding in the application code itself. That's the fundamental fix. Removing malicious code or backdoors. Attackers often leave behind web shells, injected scripts, or unauthorized files. Eradication involves meticulously finding and deleting all such malicious components.
Cleaning up what the attacker left behind.
Yes, and resetting credentials. Any passwords, API keys, or other secrets potentially compromised must be immediately reset to prevent impactors regaining access. This phase often requires tight collaboration between developers, security engineers, and sysadmins. It's about eliminating persistence.
And finally, recovery. Getting everything back up and running securely, but ideally more securely than before.
Recovery is about restoring the affected systems and data to a secure operational state, ensuring business continuity while enhancing resilience. This includes restoring from clean backups. If data was corrupted or exfiltrated, restoring from known good, uncompromised backups is often critical. Also, rebuilding hardening systems. In severe cases, a full rebuild of servers or app environments might be needed to ensure no hidden malicious components remain and apply a fresh, secure configuration.
Starting over sometimes?
Sometimes. And our deep dive materials specifically call out post-incident hardening of application infrastructures. This is critical. Lessons learned from the incident are immediately applied. It involves implementing new security controls, stricter configurations, or even architectural changes to prevent similar future attacks. This phase includes rigorous testing to ensure the application is stable, performs correctly, and is definitively more secure before going live again. It's about making the wall stronger, not just patching the hole.
It's one thing to talk about these attack types and response strategies in theory, but it hits differently when you hear about actual events. Our materials highlight some well-known incidents: Equifax, Log4Shell, SolarWinds. Looking at those really drives home the real-world impact of Layer 7 vulnerabilities.
Indeed, these case studies serve as stark reminders of Layer 7's criticality and illustrate how response strategies are developed around real-world scenarios. Examining past breaches provides invaluable, often painful, lessons.
Let's start with the Equifax breach. That was truly massive, impacting millions. What was the specific Layer 7 angle there?
The Equifax breach in 2017 was a classic and devastating example of an unpatched web application vulnerability leading to catastrophic data exfiltration. The breach involved a known vulnerability in Apache Struts, a popular web application framework. This flaw was an injection vulnerability, allowing attackers to execute commands and access sensitive databases.
So a known flaw they just hadn't fixed.
Exactly. It highlighted the devastating impact of not promptly patching known Layer 7 vulnerabilities, leading to the compromise of personal data for over 147 million people. What's crucial here is that this wasn't a sophisticated low-level network attack. It was an attack directly on the application logic and its components. It shows how easily personal data can be exposed if app defenses are weak or outdated.
Then there's Log4Shell, which felt like the entire internet was on fire when that news came out.
Yeah.
What made that such a significant Layer 7 problem?
Log4Shell in late 2021 was a critical zero-day exploit in Log4j, a ubiquitous logging utility used by countless Java applications. This was a textbook zero-day exploit targeting the application layer. Attackers could send a specially crafted string through almost any input field or header that an application might log.
So something that gets written to a log file.
Yes, and when Log4j processed this string, the vulnerability allowed remote code execution, giving attackers full control over compromised servers. Its impact was so pervasive because Log4j is embedded in so many enterprise applications. Any application using Log4j to log user input could be vulnerable. It demonstrated how a seemingly innocuous component could open a massive door at the application layer. It underscored the severe supply chain risk in software.
A hidden library causing global problems. Okay. And finally, SolarWinds. That was more supply chain, but how did Layer 7 play a role?
The SolarWinds supply chain attack in 2020 was incredibly sophisticated. While its initial compromise involved inserting malicious code into software updates for SolarWinds Orion platform.
The supply chain part.
Right. But the effects and subsequent exploitation often heavily involved Layer 7 SAP6 once that malicious update was installed. The compromised software gave attackers a backdoor. From there, they often moved laterally by exploiting application-specific APIs, web interfaces, and other Layer 7 services within the victim's environment. This was done to gather data, escalate privileges, maintain persistence. For example, using the initial access to then exploit further app layer flaws or misconfigurations like accessing cloud resources via compromised API keys.
So the first step wasn't Layer 7, but the later steps were.
Exactly. It shows how an initial compromise can quickly escalate and then heavily utilize Layer 7 pathways for deeper penetration and data exfiltration. Attackers exploit weaknesses at any link.
Wow. Each of those paints a very clear picture of just how impactful Layer 7 attacks can be. So what does this all mean? It highlights that Layer 7 isn't just conceptual. It's where the real damage often occurs, touching our most sensitive data and critical services. In the face of such diverse and complex threats and the chaos of a live incident, our research heavily emphasizes playbooks. These sound like simple instructions, but they're much more, aren't they? What exactly are Layer 7 playbooks, and why are they so vital?
Playbooks are indeed critical, and our materials detail how they're structured to provide step-by-step operational responses aligned with standards like NIST, SANS, and ISO. They're far more than simple instructions. They are comprehensive, predefined, and tested guides for incident response teams for specific types of incidents. Think of it as a detailed script for a high-stakes emergency developed before it happens.
A pre-written script for emergencies. How does that apply to Layer 7?
For Layer 7, a playbook would outline the entire process for responding to a specific attack, like SQL injection, XSS, or API abuse. They systematically cover all phases for that scenario. Detection. What are the precise indicators of compromise, IRCs? Which logs to check? With what queries? Analysis. How do you confirm the attack, determine its scope, understand its impact? Containment. Specific steps to isolate the app or block the vector. Firewall rules. WAF configs. Eradication. How to remove malicious code, patch the vulnerability, ensure the attacker is gone. Recovery. Detailed steps to restore the service, validate security, bring it safely back online.
Can you give an example?
Sure, imagine a web shell detection playbook.
Yeah.
It wouldn't just say, look for web shells. It would list specific file extensions to scan for, common web shell commands to look for in logs, and then provide a step-by-step process for isolating the server, analyzing the shell, removing it safely, ensuring no residual access.
So a playbook isn't just what to do, but how to do it, meticulously tailored. But why are these so effective? Don't they take ages to write?
That's a fair question. There's an initial investment, yes, but the practical benefits during a high-stress event far outweigh that cost. Standardizing response ensures consistent, repeatable actions across the organization. Predictable outcomes. Reducing reaction time. Eliminates guesswork, allowing faster containment and recovery. Every minute counts. Minimizing human error. Provides clear, validated steps, reducing mistakes under pressure, facilitating training. New team members can quickly learn and contribute using playbooks as guides, ensuring compliance. Aligning with NIST, SANS, ISO helps meet regulatory requirements and demonstrate due diligence.
So structure prevents chaos and speeds things up.
Precisely. Without playbooks, every major incident could spiral, leading to slower responses and greater damage. Playbooks provide essential structure, predictability, and efficiency.
If playbooks are the what to do for a type of incident, our research also talks about runbooks. Are these like the even more granular surgical instructions that live within a playbook?
Precisely. You've hit on a key distinction. Runbooks are the highly detailed how-to instructions for executing specific tasks within a broader playbook. They're the operational directives that make the playbook actionable, transforming strategic goals into tactical steps. Our sources reiterate they're structured for step-by-step response, aligned with best practices.
Okay, so playbook is the strategy, runbook is the specific tactic.
That's a great way to put it. While a playbook might say, contain the affected web server, a runbook would detail the exact procedure. For example, a runbook titled Runbook, Isolate Web Server, Server ID might specify 1. Log into F5YF console using IAdmin credentials from Secure Vault. 2. Navigate to security policies by IP blacklist. 3. Add attacker IP xxx.xxxxx.xx to high severity block list, 24-hour expiration, no reason. 4. Verify block via external test server, test VM01, confirm HTTP 4 or 3. 5. If attack persists, initiate EC2 instance shutdown for web app instance ID or 1 via AWS console, confirm success, document timestamp.
Wow, really specific steps, like a checklist.
Exactly. Or log analysis runbook for XSS might detail specific grep commands to search web server access logs for common XSS payload patterns like script or onload. Or how to interpret specific API error codes related to authentication failures to identify brute force, looking for 401 patterns.
That level of detail seems incredibly useful, almost like a pilot's checklist, especially in the heat of an incident.
It is absolutely invaluable. Runbooks enable operational efficiency, tasks executed quickly and accurately even by less experienced personnel. Consistency ensures critical steps aren't missed, actions are uniform across teams, reduced cognitive load. During a crisis, responders follow steps, freeing mental capacity for analysis. Auditability provides clear records of actions taken, vital for review and compliance.
So it removes the, how do I do this specific thing right now, panic.
Exactly. Think about a complex Layer-7 attack like sophisticated API abuse. The playbook maps the strategy, but the runbooks provide the exact API calls to block, log filters to apply, database queries to check. They drive the response engine.
Given the sheer speed and complexity of Layer-7 threats, are there ways to automate parts of this response or at least accelerate it significantly? Our research mentions automation and orchestration, often referred to as SR. What exactly does that mean for application layer security?
Absolutely. Automation is rapidly becoming indispensable, especially with the volume of alerts and the need for rapid response. As our security orchestration, automation, and response platforms are designed to streamline security operations by automating repetitive tasks and orchestrating complex workflows across various security tools. Our materials highlight that Layer-7 incident response increasingly includes SR as a core component.
How does a SOLR platform specifically help when you're dealing with Layer-7 incidents focused on application logic and data?
For Layer-7, SOCAR can be incredibly powerful in accelerating response strategies for things like web app attacks, injection flaws, XSS, CSRF, API abuse, 0 days. Here's how it works in practice. Automated alert triage. A SO platform ingests alerts from WAFs, API gateways, APM tools. If a known XSS pattern is detected, the SO playbook can automatically enrich the alert with context, check threat intel feeds for the attacking IP.
So it pulls info together automatically.
Yes, and it can even initiate a block on the WAF without human intervention for initial containment, all within seconds. Orchestrated data collection. Upon detecting potential API abuse, ASAR can automatically query various systems to gather logs, application access, database pull relevant packet captures, collect user activity data, and present it all in a unified dashboard for the analyst. Cuts down manual effort drastically.
Freeing up the human analyst to actually analyze.
Precisely. And semi-automated containment eradication. For a suspected SQL injection, a SO playbook could trigger isolation of the affected database instance or even deploy a temporary patch or fix script, as structured in pre-approved runbooks. While full eradication often needs human oversight, SO handles initial steps, buying crucial time. This allows security teams to focus on complex investigation, significantly reducing mean time to detect, MTTD, and mean time to respond, MTTR, for critical metrics.
So letting machines handle the repetitive stuff fast.
Exactly. As AI-driven attacks get faster, SR's speed and scale become essential. It's about letting machines handle the grunt work, freeing up human experts for strategic analysis.
After an incident, it's not enough to just fix the immediate problem. You need to understand exactly what happened, how, and why to prevent it recurring. This brings us to forensics at the application layer. What exactly does that entail? Is it like a digital crime scene investigation?
You've got it perfectly. It's exactly like a digital crime scene investigation. Application layer forensics is crucial for post-incident analysis and strengthening future defenses. It goes beyond simply seeing an attack. It's about meticulously reconstructing the entire sequence of events at the application level. Our materials specify that Layer 7 forensics is a deep dive, covering log analysis, packet capture interpretation, and how findings inform post-incident hardening. At its core, it's the investigative process to determine the full scope, root cause, and ultimate impact of an application security incident.
So how do log analysis and packet capture interpretation specifically become powerful forensic tools here? We touched on them for detection, but how are they used differently after the fact?
For forensics, these tools take on a deeper, more exhaustive investigative role, moving from is something happening to exactly what happened, how and who, log analysis, forensic depth. Instead, just initial anomalies, forensic analysis involves deep dives into all available application-related logs, web server access, app errors, database transactions, API gateways, authentication logs, everything. You're painstakingly correlating timestamps, user IDs, IPs, specific app functions across these logs, pinpointing the exact vulnerability exploited and tracking the attacker's path.
Building a timeline of the attack from the logs.
Exactly. Determining precisely what data was accessed, modified, or exfiltrated. Tracing from initial compromise, like a vulnerable input field, to data exfiltration by analyzing specific log entries showing unauthorized queries or file access. Building the full narrative. Packet capture interpretation. Forensic depth. This is about replaying and meticulously analyzing historical network traffic at the app layer. Understanding the precise commands, data payloads, responses exchanged. For example, understanding how exactly a zero-day payload was formatted and delivered via HTTP or API, or what specific data was transmitted via FTP post-compromise.
Seeing the actual stolen data in transit.
Potentially, yes. Packet captures can show the actual data stream, confirming what was stolen and how. Invaluable for legal and compliance reporting. Provides irrefutable evidence.
So it's about painting the full picture of the digital crime scene. And how do these deep forensic findings directly lead to post-incident hardening? It sounds like a critical feedback loop.
It is absolutely critical. The findings from Layer 7 forensics directly inform and drive post-incident hardening of application infrastructures. This is where learning is codified into stronger defenses. If forensics reveals equal injection, hardening goes beyond patching that vulnerability. It might lead to stronger input validation everywhere, deploying a more robust way, maybe redesigning database access controls.
So broader improvements based on the specific failure.
Exactly. If API abuse was detected, it might lead to stricter API authentication, more aggressive rate limiting, refined access policies based on observed attack patterns. It's about turning insights into proactive preventative measures, continuously improving resilience against web app attacks, injection flaws, XSS, CSRF, API abuse, 0 days. This continuous feedback loop from meticulous forensics to comprehensive hardening is what truly builds robust organizational readiness over time.
It feels like the digital landscape is always shifting beneath our feet. New technologies emerge, and with them, new threats. Our research projects some significant emerging trends and future challenges. What should we be looking out for in terms of what's coming next at the application layer?
You're absolutely right. The landscape is in constant, rapid flux. Our materials confirm this by projecting key emerging threats in API security, AI-driven attacks, and cloud-native application security challenges. The battleground is continuously evolving. Staying ahead requires understanding these future vectors before they fully materialize. The core takeaway, Layer 7's threat landscape is exceptionally dynamic.
Let's delve into API security first. We already discussed API abuse, so why is it still considered an emerging threat? What's evolving there?
That's an excellent distinction. While API abuse is current, its scale, sophistication, and pervasiveness are rapidly increasing, making it an emerging trend in terms of overall impact and complexity. The world is becoming profoundly API first. Every mobile app, microservice architecture, SaaS integration relies heavily on APIs. This creates an exponential increase in attack surface.
More APIs means more doors to attack.
Essentially, yes. Future threats involve more complex authentication bypasses, leveraging subtle logical flaws, exploitation of business logic within APIs to perform unauthorized transactions, and mass data exfiltration via improperly secured APIs. The sheer volume and complexity make comprehensive response increasingly challenging. We're seeing more API-specific vulnerabilities needing specialized detection and response, demanding specific playbooks structured around API interaction patterns.
AI-driven attacks sound almost like science fiction. How exactly does AI factor into Layer 7 threats? How does that change the game?
It might sound futuristic, but it's very real and already starting. AI is truly a double-edged sword, used for both defense and offense. On the offensive side, attackers are increasingly using AI and machine learning to automate parts of their attack chains. Sophisticated reconnaissance, mapping attack surfaces faster than humans, generating highly convincing personalized phishing campaigns, harder to spot.
Smarter phishing. Okay. What about Layer 7 specifically?
Crucially for Layer 7, AI can identify zero-day exploits more quickly and even adapt attack patterns dynamically to evade traditional detection systems. Imagine AI-powered bots dynamically crafting injection flaws or API abuse attempts, constantly learning from application responses and evolving their attack vectors in real time.
Bots learning how to hack better.
That's the potential. An AI could analyze an act's behavior and automatically generate highly effective XSS payloads that bypass specific WAF rules, making manual detection incredibly difficult. For your personal security, this means keeping software updated isn't just a good habit, it's a race against automated, intelligent threats. This will necessitate equally sophisticated AI-driven defenses, a constant arms race. Response strategies will need AI-powered detection and autonomous response elements.
And what about cloud-native application security challenges? What makes those distinct from traditional app security?
Cloud adoption fundamentally changes the security perimeter and introduces new complexities. Cloud-native apps often use microservices, serverless functions, containers, vast API networks. This creates new challenges. Pervasive misconfigurations in cloud security groups accidentally exposing services, insecure container images carrying third-party vulnerabilities, flaws in serverless function code.
More moving parts, more places for things to go wrong.
Exactly. Plus, complex identity and access management across multiple cloud services. And the ephemeral nature of some cloud components' resources spun up and down rapidly complicates traditional forensics and logging. Evidence might disappear quickly. A single misconfigured S3 bucket or an exposed Kubernetes API could lead to massive breaches. It's securing an entire ecosystem of interconnected, rapidly deploying services communicating at Layer 7.
So with all these complex threats from classic flaws to AI attacks and cloud challenges, how does an organization truly prepare? Our research really emphasizes building organizational readiness. What does that mean in practical terms for Layer 7 security? It sounds like the culmination.
Organizational readiness is truly the culmination. It's about establishing a mature, proactive security posture, ensuring that when a Layer 7 incident occurs, the organization isn't caught off guard and can respond effectively. Our materials highlight this explores developing robust responses aligned with NIST, SANS, ISO. Fundamentally, it's the holistic effort to ensure an organization can effectively prevent, detect, respond to, and recover from any Layer 7 incident.
What are the key components of this readiness? Is it just about having the right tools?
Far more than just tools. It involves several integrated aspects working together, developing comprehensive incident response strategies, specific detailed strategies for web app attacks, injection flaws, XSS, CSRF, API abuse, 0 days, regularly reviewed and updated, creating and maintaining robust playbooks and runbooks. These are living processes, tested and refined, aligned with standards for every critical Layer 7 threat.
The plans and the checklists we discussed.
Implementing advanced detection and monitoring. Continuous log analysis, packet capture, supported by SIM and SOAR platforms for real-time identification. Prioritizing post-incident hardening. Security isn't static. Every incident is a learning opportunity, a structured process to implement changes based on forensics, continuously improving infrastructure.
Learning from mistakes to get stronger.
Regular training and exercises. Teams must be trained. Tabletop exercises, simulations help practice response, identify gaps, improve coordination under pressure, making response second nature, fostering a security-aware culture. Everyone plays a role. Developers writing secure code, end users vigilant about phishing. Security is everyone's job. Staying informed on emerging threats, continuously monitoring API security trends, AI attacks, cloud challenges to adapt defenses proactively.
So it's technology, process, and people.
Absolutely. Organizational readiness isn't a one-time project. It's a continuous cycle of planning, implementation, testing, improvement, a deep, ongoing commitment to protecting critical applications.
It truly sounds like a marathon, not a sprint. A constant evolution of defenses and response capabilities is absolutely essential in this digital age. What a deep dive. We've really peeled back the layers of application security today. From understanding the fundamental protocols like HTTP, DNS, and APIs that power your daily digital life, through the treacherous landscape of web application attacks, injection flaws, XSS, and 0 days, all the way to the critical frameworks, playbooks, and forensic methods that organizations employ to keep our digital world safe.
We've seen how major incidents like Equifax, Log4Shell, and SolarWinds dramatically underscore the pervasive nature of Layer 7 vulnerabilities. And crucially, we've explored the vital role that structured incident response, meticulous detection, and continuous post-incident hardening play in protecting our data and services. Looking ahead, the future promises new challenges with API expansion, AI-driven attacks, cloud complexities. This makes building robust organizational readiness not just an aspiration, but an absolute necessity.
You've now got a much clearer, more nuanced picture of where many cyber threats actually land and the sophisticated ways organizations are fighting back. Understanding this isn't just for security professionals. It helps all of us appreciate the complex engineering behind the apps we use every day and why robust security practices are paramount for everyone.
This really raises an important question for all of us. With applications constantly evolving and new threats emerging daily, how regularly are your application layer defenses? Whether that's your personal software updates, your business's incident response plans, or your understanding of digital risks being tested and updated. And what proactive steps are you taking to foster a more secure digital environment in your own sphere, but personally and professionally?
A compelling thought to ponder as you navigate your digital life. Thank you for joining us on this deep dive. Until next time, stay curious and most importantly, stay secure.